questions or comments? Yeah, Mark.
Sasha.
During your talk, I had a feeling that, you know, the attitude to study nonlinear equations, the fields, the solitary waves, etc., changed with time. Because at the beginning, when you described to us works of Korteweg, De Vries, you know, all this, they were really concerned about asymptotics and about, you know, control over the derivation. So they were responsible, they can control everything. Now when you go to this nonlinear optics, it seems that you try to add and, you know, tweak some terms in order to satisfy some experimental phenomena, and then you don't have any control whatsoever on this equation. It's just, you know, it's like you try to assemble some puzzle. And is it true?
Partly true, not completely true. Okay, if you take communications, the derivation of the key equations are quite rigorous from Maxwell's equations. But then you start putting in amplification and damping, and that's when you have to put in some, you might say, experimental work. Because in communications, damping was studied very, very carefully over many years. So they understood that it was linear damping. If you go to lasers, I think, in fairness to House, he had a pretty good feeling for the kinds of terms that needed to be there from the amplification point of view. From the damping point of view, which is what we call the power, the saturation of power, that's a little bit harder, and what I use there is generally an approximation. I think if it became important to physicists, they would start looking at those terms and do experiments over a period of years, and then nail it down like they did in communications. In communications, well, damping, linear damping was studied because there was commercial interest, so that was nailed down in the early days. It was linear damping and good approximation.
Even about this equation you quoted, which is Gabitov and Kuritzen, and you probably discovered a bit later. I spoke to Gabitov and Kuritzen and asked, do they have any control over asymptotic, whether really give asymptotic, or it's just some model which captures the main phenomena? They believe to, and I think they didn't give me any good argument that it's really asymptotic in the mathematical sense.
Okay, so in a mathematical sense, first of all, what they used was Hamiltonian methods. We used multiple scales. Not only did we go to first order, we also went to higher order and compared with the underlying original equations, found it very accurate, and then came along a group, I have it, Zharnitsky and Jones and those guys, and they proved rigorously that the DM and LS equation was asymptotic. Not only did they prove that, they also proved rigorously that the solitary waves were stable, orbitably stable. So it depends. There was a lot of interest in dispersion management, so people studied the asymptotics and the rigorous mathematics. And the answer is, rigorously they are stable, rigorously it is an asymptotic theory. But that doesn't say it's asymptotic back to Maxwell's equations. It just says the original equation with d of z and n of z leads to an integral differential equation, and that approximation is asymptotic.
Okay, maybe we can continue this discussion in the coffee break. Other questions or comments? If no, let's thank our speakers again. And we'll have a coffee break and until 10:30. Thank you.